Okay, so in this lecture, I'm going to construct few more automatas for practice. In last lecture, we have seen few languages, like if a language is starting with some specific symbol or ending with some specific symbol, how we can design an automata. Now this language which I have taken here, the language of all strings over the alphabet A, comma B, that contains the substring AA. So that means whatever the number of strings we are generating, here I am assuming that the set of alphabet is A, comma B. Okay, so we need to define the strings over A and B only. So this language may have, if I define this language may have smallest string as AA. It cannot have null, right? And then it may have AAA or BAA, because substring AA is compulsorily there. Then it may have 4 length or 5 length or 6 length, but somewhere AA will come. That is the meaning of this language, right? So if this is the language, how we can construct the automata for this? So let's draw the automata. Let's say Q0 is the initial state. Now what we have to do? What we have to do in such a problem, when a substring we need to, we have given that every string is having a substring. So first draw the automata which will accept that substring, right? So you draw the automata. Let's say AA is the substring. So first I am drawing it, an automata which will accept AA. Okay, so from initial state, when A is coming, I am reaching a state. Let's say this is my new state. Let's say Q1, but Q1 cannot be final because I am going for one more A. So this is another A input, and let's say I am reaching the state Q2. But Q2 can be final because AA string can be generated in this language. So I will double circle it. Okay. Now this automata, this is, as of now it is non-deterministic because there is no transition I have defined for B. And in the definition of deterministic, we know that if there are two input symbols on every state, there has to be unique transition for each and every input symbol. So let us improve that. If B is coming, B may come in the beginning. So for B, we can put a loop. It's not a problem, right? Still, so this automata will generate B n number of times, then AA. So that means every string here is ending with AA. Now with every string is ending with AA, it is not the constraint because the strings like A, B, B will also be generated or accepted in this particular language. Okay, so we need to add few more, but we need to take care about two consecutive A must come. Two consecutive A must come. So after A, let's say here, if B comes, better to go backward. If you apply here loop, then there will not be any guarantee whether A is coming consecutively or not. So if B is coming here, I'm going back, right? So B n number of times it may come, maybe 0 times or n times. Then A, if any B comes here, I will go back because I want two consecutive A's. Here anything can come, maybe A or B can come, right? So if I ask whether this is deterministic or non-deterministic, you check. On Q0 there is a unique transition for B, unique transition for A. On Q1 there is a unique transition for A, unique transition for B. On Q2 there is a unique transition for A and B. So that means it is a DFA. Okay, right? So I hope now you can construct any automata where a substring is given. Okay, so let's discuss one more. So if I take this language, Here the set of alphabet I am assuming the same. The set of alphabet is A comma B only. Now the language is all the strings over A comma B that contains the substring ABA. So again the same thing you need to do. You start drawing the initial state. Then first draw the automata which can accept ABA. So first A, and let's say there is a string new state Q1. But this Q1 cannot be the final, because if this will be the final, only single A can be accepted. Then let's say B is coming here, so you are reaching Q2. Q2 can also not be the final. Then let's say A is coming and we are reaching to a new state, that is, let's say Q3, and Q3 is the final state, so it is double circle. So now this automata can accept ABA, but we need to refine it. We need to add some more transactions or edges in this. So on Q0, because we are intended to draw a deterministic finite automata, which should be minimal in number of state also. So later on I'll discuss how to minimize an automata. If you are drawing an automata randomly and if it is not minimized, we can do it. Okay. So for B there is no transition on Q0, so I can put a loop on Q0 for B, right? But if anything comes here, let's say A comes, if A comes, you may apply a loop of A here, because once A comes, ABA, still the string will exist. Okay, or for A you can come back also. So because we need to maintain ABA substring, so if you put a loop after coming A, if you are traversing A n number of times, still if you continue further, this ABA will be there, right? ABA will be there, so there's not a problem. So I may put a loop of A, or I may draw something like this. Now here after B, if A comes, you are moving at Q2, Q3 on Q2, but if B is coming, better you can go here, because after A, if B comes, and if you are reaching here, if you go here, then there may be a problem, because ABA you cannot ensure, ABBA you may have, so better to go back here. Okay, I hope you are able to understand it. So if I am getting B, I am going back, right? Now here, whether A is coming or B is coming, I am putting it. So this is one of the possible automata which can accept this particular language, right? So any substring, if it is given over any alphabet, like binary alphabet like A, B or 0, 1, you can easily draw a deterministic finite automata, right? So this is sufficient for the lecture. We will draw few more automatas. I am giving the list of regular languages. For that you can draw the automata at your home. So in description section I am giving somewhere around 50 or 54 languages. Later on I will add a few more languages, so you can draw the automata for each and every one. I'll try to draw the automata for most of them, the important one. Okay, so thank you everybody, see you in the next class.